Hello and welcome to the Daily Space for today, Thursday, October 16th, 2019. I am your host for today, Dr. Pamela Gay, and I am here to put science in your brain. Today we have a variety of news stories coming to you from all over the solar system, but our first story comes to us from Mars. This is mostly a pretty picture story, and in this case, the pretty picture comes from the Mars Reconnaissance Orbiter's high-rise camera, which has been studying the Eleusis Planitia of Mars, looking for the kinds of, changes that appear when dust devils sweep through the area or other things occur. Now, while trying to accomplish these science goals, HiRISE was also able to, capture this amazing image of the InSight lander and its surroundings. When InSight came in for a landing, it was using descent engines, and those descent engines blasted out an area around the lander, removing all of the lighter colored dust and debris that normally covers the surface and revealing this darker region. In this image, which you will be able to see a high-resolution version of on our website later today, in this image you can make out the InSight's two large round solar panels. You can also see the glint off of the cover for the InSight seismograph. Now, while this isn't the most scientific of images, it is just kind of cool to see, what our landers look like when they're sitting on another world. These kinds of, orbital images looking down at our rovers and landers also provide context to the science that's being done down on the ground. This is particularly important with the roving Curiosity rover. Currently, the Mars Science Laboratory is roving its way through Gale Crater on a way to visit its central peak, Mount Sharp. As it goes, it has to beware of sand dunes and other hazards that litter the floor of this crater. With this particular animation, it's possible to see, let me see if I can zoom in on this for you. It's possible to see how the rover has moved through the crater, avoiding hazards as it goes. Now, images like this, we take them to give context to the science, but we don't currently have the science to give you. This is just a sneak peek of what is yet to come. And it also helps us understand just what are some of the decisions being made by the Mars driving team as they figure out how to, set this rover roving. Now, our next story is also one that is rich in pretty pictures, while kind of devoid in science. This is the latest imagery to come to us of Comet 2I Borisov. As this extrasolar comet makes its way through our solar system, I kind of expect almost daily updates. I will not bring you all of these updates. I'm bringing you this one because, it's just kind of cool to see this animation as the comet zips past all the different stars you see trailing behind it. This animation was created with a series of Hubble Space Telescope images that once again show us this comet is absolutely ordinary. Now, in the coming months, Comet Borissov is going to be coming toward us from below the plane of the planets, from below the ecliptic. On December 7th, it will pass as close as it will get to our sun. At this point in time, it'll be fairly close to the planet Mars, and Earth will be most of the way around the sun on the other side of the solar system. Now, thanks to the geometry of this comet's motion through our solar system, coming up from below and passing out through the top of the disk, it will spend very little time hidden from us by the sun. And, it's just going to be a wild ride as we look to see if this comet ever decides to show itself as extraordinary. For now, It's average, and that is kind of scientifically awesome, if boring. Well, moving on to another story of solar system science. This one is one that I actually picked up from our colleagues over at space.com, and it covers new discoveries that were made at the University of Hawaii, Manoa, and published in the Astrophysical Journal Letters. In this particular piece, they're trying to understand how it is that so many icy worlds in our solar system have extraordinarily complex polycyclic hydrocarbons on their surface. These molecules are the kinds of things that we experience here on Earth, and they get their name from the fact that, well, you can detect them with your nose from their strong odors. In this particular image, we're seeing sand dunes across the surface of Titan. And in these sand dunes is one of those places that we have detected these complex polycyclic hydrocarbon molecules. One way that it was theorized that these molecules may be forming is that everyday ices that are made up of simple organic molecules are getting struck by galactic cosmic rays, and the energy imparted by those cosmic rays is able to go into the formation of these complex molecules. To see if this is what's going on, laboratory scientists took a block of acetylene ice and bombarded it with 100 years worth of cosmic rays to see what would happen. Yes, they radiated a block of ice. Now, acetylene is a molecule made up of triply bonded carbon and 2 hydrogens, so that's C2H2. In this particular experiment, they found after all of those cosmic rays bombarded the acetylene ice, they did indeed have polycyclic aromatic hydrocarbons. That's a mouthful to say. Now, it's unclear exactly how close their process resembled that of what's actually going on icy bodies, but this is a start to understanding what's going on. Further research is needed to understand exactly what energies of cosmic rays are the ones that are triggering the formation of these molecules. And of course, they have to figure out if the same thing happens when the incoming cosmic rays come in at a slower rate, where those 100 years are experienced over 100 years instead of the much shorter period of time that they ran this experiment in their laboratory. It is nonetheless cool, and just goes to show you that sometimes laboratory chemistry here on Earth can help you understand the outer solar system. Now, in our final story, we have one of massive galactic proportions. In this case, we're actually talking about super spiral galaxies. This is a new kind of galaxy that has recently been found in the Sloan Digital Sky Survey. And these systems, of which there are only about 100 known so far, are rotating at rates never before observed for spiral galaxies. These systems, we had previously known that elliptical galaxies, spherical galaxies, come in all sizes, from the dwarf ones that that our galaxy constantly eats, all the way out to the massive ones that sit in the centers of superclusters. We'd thought, however, that spiral galaxies like our own and Andromeda have a much more narrow range of sizes that they come in. This has to do with our understanding of how they're formed. These 100 or so systems do not meet what we had expected and are significantly larger, tens of times larger, and appeared to exist inside massive dark matter halos. Now, in order to figure this out, once these systems were found using the Sloan Digital Sky Survey by looking at them and seeing they are spiral galaxies, scientists used the Southern African Large Telescope, SALT, to measure the rotation rates of these systems. And it's from the rotation rates that they were able to derive the anticipated mass of these systems. Now, one of the cool things about this research is these systems appear to have fewer stars than would otherwise be expected. And that indicates three things, actually. It indicates, first of all, that dark matter is a thing, and we're not worried about modified Newtonian dynamics much anymore. This is because if the reason that we're seeing a rotation rate that implies the existence of invisible matter was not due to invisible matter, but instead due to an extra term of gravity, then what we see in regular spiral galaxies would just scale up for what we're seeing in these massive spiral galaxies, but it doesn't. Instead, what we refer to as the mass to light ratio, the observed mass implied by the rotation of these systems, it seems to say that there's significantly more invisible matter in these systems than what we see in our own system. So if it was just an additional term to gravity, things would scale up. You'd see the exact same mass to light ratio across both sizes of systems. We don't see that. More, nails in the coffin of modified Newtonian dynamics. In addition to that, this also seems to imply, there's an additional formation mechanism, which is cool. And third, it implies that there's something going on in these systems that is preventing star formation at a certain level. Now, these systems are massive. They're much larger than our own system. We're seeing star formation rates that are 30 times what we have in our own galaxy. But what we see in terms of stars is still too little. And that seems to imply that either the massive gravity of the system is crushing the gas so much that under that pressure it's so hot that stars can't form, or the rotation of the system is so great that the kinds of collapses that we see leading to the formation of open star cluster star-forming regions like the Orion star-forming region, these kinds of star formation mechanisms are limited in a system that's rotating so fast. More observations are needed. And this is the kind of system that is desperately awaiting the launch of telescopes like WFIRST and the JWST. These kinds of systems will hopefully allow us to study more and get a better understanding of how this remarkably rare kind of galaxy fits into the bigger picture of the evolution of our cosmos. And that kind of closes out our stories for today. I will now hang around and answer your questions. And while you are typing them in, I'm going to remind you once again, it ate all of my comments. No, it doesn't. There it goes. Okay. I seem to have a gap in my chat. If you typed in questions, please copy and paste them back in. My phone went to sleep and ate the chat. Okay, so please go ahead, type your questions in. Precede your questions with that big purple circle with a star inside of it to help me find your questions. While you type them in, I'm going to remind you the Daily Space comes to you most Mondays through Fridays at 1 p.m. Eastern, 10 a.m. Pacific. That is 6 p.m. London time. We are produced by Susie Murph, and we are a production of the Planetary Science Institute, a 501c3 dedicated to the exploration of this solar system and beyond. We are brought to you by you. We are able to pay Susie and Annie to be part of this show thanks to your bits, your subs, your donations, and most of all, your patronage over at patreon.com/CosmoQuestX. If you would like to help us out, please consider giving, especially as we are running out of 2019 and you still have a chance to get a tax deduction by donating. That's all I've got. If you can't give, we totally understand. Spread the word. Get someone else watching. Get someone else listening to our podcast, The Daily Space. You never know whose life you're going to change by introducing them to science. Okay, now I'm going to see what questions I can see. Okay, here we go. Hanny asks, could the black hole at the center be causing stars to form slower? It must be enormous. So active black holes can squash star formation by giving off a blast of, it's not from the black hole, the accretion disk around an active black hole will give off so much energy that it pushes away the material that is falling in, triggering a massive round of star formation that then uses up all the materials available for star formation. These aren't active systems, at least not as far as what I've read so far, and so it's unlikely that the black hole is the culprit in what we're seeing. So Fenmil says, sand like on Earth, sand, or something different sand? I need more words, Fenmil. What sand are you speaking about? So Larry asks, what is the time duration of the Hubble animation? This would be the animation of Comet Borissov. I don't know the exact duration based on how much motion is going on. This object is moving fast, but not that fast. I'm guessing that this is a series of images taken over several days. But that's a guess. I would have to go look at the press release. Looking to see what other questions. Larry is asking, will Curiosity summit Mount Sharp someday? It's not currently scheduled to summit it because that might be a bit dangerous. But you never know, given that these rovers tend to be capable of far more than we usually suspect. Now, Curiosity is going to have much more of a finite end to its existence than we had with Curiosity and Spirit and Opportunity. Spirit and Opportunity were powered with solar panels, and as long as the solar panels kept clean, the rovers were able to keep going, and it was actually dust storms and dust that appeared to have killed off Opportunity. With Curiosity, instead, we're dealing with a nuclear drive, a radiothermal generator. And as those radioisotopes stop decaying, because they've all decayed, the RTG is going to be producing less energy, and that will put a hard cutoff to the end of Curiosity's functionality. But here's to hoping it lasts longer than expected, and as they've done with other rovers, they take on more dangerous exploration than is currently planned. Henny asks, are galaxies this big supposed to be elliptical? Well, it's not so much that galaxies as large as the superspirals that we're talking about are supposed to be elliptical. It's that so far the only ones we've seen have been elliptical. And because we're scientists, we base our models for the universe on what we have seen. And sometimes in order to get from point A to point D, you have to theorize the points in between. And that's how we figure out things like the predictions that went into understanding if there was a Big Bang, then you would see the cosmic microwave background that allowed Penzias and Wilson to understand what they saw when they saw it. Now, when we look at the universe, we've only seen elliptical galaxies at this size, so our models all figured out how to make elliptical galaxies of that size, and our models for making spiral galaxies were able to explain the spiral galaxies that we see. This is new. We haven't seen it before, and so it's not what is the universe supposed to be, it's what did our narrow thinking as humans lead us to believe was out there, and our narrow thinking didn't lead us to predict these particular large galaxies. So Hanny is asking, is the sand made of polycyclic hydrocarbons or contaminated? So the sand itself, I don't know what all it's made of, but it is contaminated with polycyclic hydrocarbons. So they find evidence for the polycyclic hydrocarbons in what they refer to as splotches on the dunes, splotches on the ice of other worlds. So it's not just the sand is made up of these materials, but the sand is contaminated by those materials. Thanks for making it more clear what the question is. So Fenwell asks, most of the sand on Earth is from erosion and takes a while, if I recall. So do they think that Titan sand is from erosion, and clue as to the composition? Again, I don't actually remember and may not actually have ever known what the sand on Titan is made of. It could be and probably is made through erosion processes. This is a icy world, and you can end up with sand of ice if you consider sand as simply small granular things that are able to flow as sand dunes. So it's the texture that I'm referring to when I call it sand. Titan does have storms, winds, rain, ice. So it's probably very similar erosion processes, but it's made with different chemistry than we have here on Earth, because here on Earth we have higher gravity, and water fills the role that liquid methane and liquid ethane form, or rather fill, on Titan, which is lower gravity and colder. So similar processes, different liquid involved. So Broken Symmetry is asking, when you have your marathon podcast for funding, can you invite the awesome astronomy cast to join in as guests, as well as other 365 days of astronomy alumni? Yes, that actually is part of the plan. So we will be doing another Hangout-a-thon this year in December. Our goal is to make sure that we have enough funding to keep all of our media programs here at CosmoQuest going and to pay for all of our servers for another year. We will be doing this the weekend before Christmas, and we are in the process of recruiting or getting ready to recruit guests. I'm sure Fraser and I will be on, as we always are, and I will be extending an invitation to the 365 Days of Astronomy podcasters. Keeping 365 Days of Astronomy going is part of that Hangout-a-thon. Hanny asks, isn't water more solvent than methane? It is, but that doesn't mean that methane can't do the same thing. It just means it's a little bit harder. So in general, sand is made when materials are rolled, wet, all these other complex processes basically ground together through weather and wind. So combination of rain, blowing, cracking from heating and cooling, all these different temperature fluctuations, and, well, water falling out of the sky and wind blowing across the surface. All of these things work to decay surfaces. Other questions? Oh, Hanny is asking, how did the grant writing go? So grant writing is a continual process. So far this year, I've put in one grant as a principal investigator. The main deadlines for the year are coming up in November. I'm going to have another large grant going in then. I am also part of additional other grants. And I'm not going to detail out grants led by other humans, but we have put in and are in the process of putting in a total of 4 grants where we are part of other people's funding sources. Grant writing is always hard. On the best of days, you have 1 in 5 proposals is selected. On a bad day, 1 in 25 is selected. And it's to the point where you can have a completely excellent proposal, but what you're proposing to do doesn't fill out the suite of things that the government is looking to fund at any given moment. So it's a complicated time, and we're not sure what the outcome is going to be, but we're working hard to keep going and to keep things going here for you. Funding is always bleak to discuss. Anyone have any more cheerful questions to ask? Oh, come on. My phone keeps putting on its screensaver. If you have no more questions, I am going to go and record our podcast, get that posted. Please consider subscribing to it if you haven't. This will really help people find us. It's Daily Space. You can find it in any of your favorite podcast directories. Beyond that, thank you, Trekker Kev. Oh, Falco, I'm sorry that you're late. Come on up. Someone just wanted to see Eddie. This is Eddie. He gets treats in exchange for all of your happy bits. Hi. Hi, I love you too. You're so good. And he would like to eat Benno, apparently. Hi. Hi. I know. I'm going to, go do all the other things that need to get done around here. So wherever you are in the world, we all share one sky. In the universe, we can understand it with science. And that's all kind of awesome. So the Daily Space comes to you most Mondays through Fridays at 10 a.m. Pacific, 1 p.m. Eastern, 6 p.m. London time. We will be back tomorrow, and following this, we will have an hour or so later, astronomy cast. So stay tuned, put it on your calendar. Until then, wherever you are in the world, have a fabulous morning, evening, or afternoon, and I will see you on the other side. Bye-bye.